Okay, hello everyone, hello Moody. Just to give you guys an impression of what we're doing, given the current half lockdown of the Netherlands, we're going to record this lecture. I'm here with Mohammed.
Hi.
And well, we're going to continue the software engineering courses. If you remember where we ended up last week, well, 2 weeks ago now, we ended up to the definition of a monoid. So let's recap quickly. So we know that a monoid in the domain of simple types, so the simplest kind of monoid we can think of, has a type T, could be, let's say, number, a single element E of type T, let's say, for example, 0, and then a join operation that takes as input 2 T's, like plus, and returns another instance of T. Now, if you look at it this way, it means that the monoid has a recombination operation, join in our case, and a neutral element. And if these elements and the join operation together respect the monoidal laws, specifically that joining the neutral element with anything on both sides gives us the anything we chose, and also that it doesn't really matter in which order we join 3 elements 2 by 2 to collapse them into a single element, then we say that we have a proper monoid. What does this mean? This is where it gets slightly interesting and a bit philosophical if you want. So it means that there is a special element that doesn't really add information with respect to joining. So if you join, you are typically trying to combine the information of 2 elements into one. But if one element doesn't really get you anywhere, then it means that there exists an element which represents lack of information in the domain T. And if you think about it in this very simple example, 0 represents lack of information with respect to addition. Also, the existence of a join operation means that the type T is big enough that it doesn't matter how big or 2 elements you choose to add, you still remain inside the domain of numbers. It means that you're never going to run out of numbers. It suggests this ability to recombine without losing structure or without having the need for more structure. Okay, so monoids are quite important because this ability to combine is essential. This ability to combine and remain inside T means that, well, you can join and you get a T, then you can join again, you get another T, then you can join again, you get another T. And this is very important to us because this ability to combine things together without leaving the original domain gives us the ability to write programs that are as big as we need, instead of, I don't know, that you can join 3 times, but you can't join a 4th time because, well, then you're done, you're stuck. It's very important. And the fact that we have a sort of rock bottom element is also very important because it means that we start somewhere. Now, but then we suggested in the last lecture that this formulation here, it is appealing, it is intuitive, we understand it, but it's somewhat limited because the only constructs we've been discussing in the course are, for example, functions, which are composable. We've discussed functors, which are composable structures. We also know that we can take 2 functions, and we can make a composed function out of them. And it's just a normal function, you know. At that point, you simply get a function. You have a to b, b to c, and you get a function a to c, and that's a normal function. And you forget that there's a b in between. And that's important, this composition property. And then we had functors, and we've seen that functors are the structures with map. But those are also composable. You can take 2 functors and you can compose them together. And it's nice because their map function can be composed as a normal function, leading us to the map function of the composed functor. So these are important structures, and the fact that functors are defined and their composition is defined in terms of composition of functions is essential because it shows us that we are on the right track. If you look at monoids from this perspective, I mean, they are understandable, but, well, element E is just an element, it's not a function. We can't really compose it, we can't really do much about it. And the join operation, well, it's not really a function in the sense that we need, because it has two parameters, and we've been dealing with functions with only one parameter, and that's essential for the composition. So we suggested, okay, you know what? Let's reformulate monoids in terms of functions. Why? Because we want to force ourselves to stick to the framework that we've defined. So we want to only use functions, and we want to stick to function composition. So we say, okay, I called it last time a proper monoid to still be a type T, but then the element, the neutral element, instead of saying give us just one T, we say no, let's get one function that picks the neutral element. So this function doesn't really get an input, so you can only call it with unit, and unit has a single value, which is the empty record, the curly brackets. And you give it unit, and it gives you the 0 of the monoid. And this is a function. Then we have the join operation. And the join operation, we formulate it as a function from a pair of two T's condensed together. So instead of giving first one T, then the other T, and then we get the resulting T back, in this case we say no, first you create a pair with both T's inside, then you give it to the function, and then you get the single T. These two, and these two definitions that we have here are exactly the same, literally exactly the same. And then we reformulated what happens when restating the monoid properties on this new definition. And here we started with join of EX is equal to join of XE, which is equal to E. And we don't have E anymore, so E we have to call eta. And that's the same as E, because eta, when you call it, it always gives you back E. It's the function that knows how to give you E back. Then we make a pair where the first element is eta and the second element is X, and we join. And we know that this is the same as X. And the same happens if we put eta in the second element and the first element is X, and we join and we get X back. And the very same thing is here when we're looking at the associativity of monoids. It's simply the order in which we create the pairs and in which we join the operations, and in which we perform the joins. So that's the same. Yes, so, and this is just a reformulation, but we're just playing around with the concept. Now, let's do an exercise which actually happens to be, oh no, first of all, let's define the numbered monoid on the sum monoid on numbers in these terms. So we would say eta sum would be a function from unit to number, just to give you an impression of what these things do. And this is a function, takes as input eta, sorry, takes as input unit, and I don't even need to give it a name, and gives us 0 back. Is it happy? Why is it not happy? Oh, because I need to declare in this case that this is unit. Oh, obviously, no. Sorry, it's been too long. We don't need to declare it. We need to put it in the func constructor. Yes, okay. Now it's happy. And then we have that join sum. Well, it takes as input a pair of number and number, and it gives us a number back. And what is this? Takes as input the pair. I will call it xy, so both x and y, the arguments, and then we simply return xy dot first plus xy dot second, and that's it. And if we were to define this same monoid, now we would say that the neutral element of the sum is, well, you could even say, and this has to be a number, you could even say, now you know what, let's use eta sum, let's simply call eta sum with nothing, and the join of the sum in this case, and now we want it to simply be a function from two numbers into a number, we could say, okay, it takes as input x, which is a number, y, which is a number, and then it has to return a number, and we could say x plus y, or we could show that we could simply call join sum.f, and we pass it, first is x, second is y. These two definitions are just basically a syntactic transformation of each other. And you could also define eta sum and join sum in terms of the other two. So you could also do it the other way around. You could say that eta sum here, it returns e sum, and here we simply call plus sum of these two elements. Okay? So again, I really want to stress the fact that these two are exactly the same definitions. Okay? But, so, if we go back to these equality relations, that's a bit of a snag, because now what we're actually saying that these two lines are not really acceptable, as a matter of fact, because they are forcing us to define a notion of equality of values, which we don't really have. Also, so what I'm going to do is I'm going to take this notion here of equivalent of values and turn it into an equivalent of functions. Because to be correct, here we should have said that for each x that belongs to t, then this is true. So this is chaotic. We're also introducing the notion of for each and belonging to a set, etc. Whereas we already have a perfectly good framework of functions. So how do we reformulate this now in terms of constructs we have already available? Now, we could say that, well, first of all, let's turn these things into functions. So this is x goes into join blah blah, and this is x goes into, and this is x goes into, right? So now I'm saying that this function here has to be the same as this function, which has to be the same as this function. I'm going to claim another line in the code. Yes, sir. Okay. That's still the same. Now I'm stating that this function, which doesn't know which x it takes as input, is going to join x with eta, and eta is going to be on the left side. And this is the same as the function that takes x and simply gives x back. It means that what this operation does is give you x back. That's the same. But now I'm simply saying, okay, instead of having this vague notion of for every value of x, which doesn't really mean much, I'm saying, okay, no, you have a lambda, and this lambda, yeah, it doesn't really matter which x you put in, you get the same x back. So now I'm using functions to cover the concept of for each value of x. Now, I'm going to reformulate this in terms of function composition. Why function composition? Well, function composition because, well, what's the order of composition here? Think about it for a second. So what's happening first and what's happening second? Eta is happening first, and the join is happening second. So you could say, okay, we take eta, and then we could say that we have eta, then, and then we have the result of eta. I'm going to call it e because that's the same as before. Then I create the tuple, and well, that's what I have now. But you could also say that you create the pair. So let's say that we define a function, make pair, a generic function which has type. No, actually, make pair. No, let's yes, to make a pair, we have two generic arguments, and then we return a function that takes the first element of the pair, then returns a function, takes the second element of the pair, and then gives us a pair of A and B. Yes. Did I miss? Yes, I did miss one. Now, let's see if the compiler is happy now, before I end up. Oh, obviously, yes, okay. Now, I'm simply defining here, making a pair by giving first the first element, then you give the second element, and then you get a pair with currying. So now I get the first element, I'm gonna call it A, and then what do we give back? A function that takes the second element, we call it B, and finally, well, at this point I can simply build up the pair. There's not really much I can do. And the second is B, yes, okay. So now, I have E, and also have X. So you could say that we call first make pair on, well, what do we want to give? We first want to give E, then we give X, and then we join. Right? Okay. And the very same thing could be done at this level. So I could also throw this away and rewrite it in the opposite order. So first X, then E. And now you notice that we are able, by redefining things into functions, now there is a little bit of awkwardness left, but this is a composition framework. So we are simply building the function exactly as we're supposed to do it. And that this composition of functions, well, if you find something like this, you might as well skip it because, well, that's the identity. The same thing could be done here. That's roughly the same. So you would define this join, and then this join with a bunch of make pairs in between. So by moving to the functional framework, we have discovered that our equality laws can be defined in terms of composition of functions, so can be brought back into the fold of what we have seen already, instead of claiming completely new concepts. This shows us again that we are on the right track, because whenever we have to introduce new exceptions, well, that's an issue because we're making our framework bigger and heavier, and we have to take these exceptions with us until the end of days. And I mean, we just literally started. We have functions and composition, we have functors and composition, we have monoids. We don't want to define a new construct just because we're too lazy. And we want to have monoids, and so we say, okay, we need a new construct, and then like Java language designers, you add a new keyword to the language. We don't want to add keywords to the language. We only want to do it if there is no alternative. So we like this because it makes it possible to add less to our framework. Okay. So now that we have this formulation, which is more generic and it is more idiomatic with respect to our constructs so far, we are going to turn this definition here into a definition that also works with functors. So, because we also have functors, but right now there are no functors. But functors, ideally, are a good candidate to generalize any construction in which we also have types. How? Now, a functorial monoid is a a monoidal functor is a functor f. Then we have now, so obviously whenever, so I'm going to start by saying, okay, now we need to put f wherever we had t before. But obviously this doesn't make any sense, because I can't define an element eta that gets a unit as input and gives f back. So you can't really get f back. It doesn't make any sense, because f is a functor, so it's a generic type. So you could say it goes into f of a. It could, but it's a bit weird because, well, if we transform one side of the function, we kind of expect to transform the other. Now, if you look at this definition here, well, this definition is basically a default constructor. So we need a default constructor for a type. And it makes sense that when you're instantiating a type, now you don't really know what, you can't force an input. You can't say, okay, you get a number and you put a t in here. So if t is string, what's a number? You don't know. So here we're saying, okay, you know what, for the default constructor, we need to get the least amount of data that makes sense to build this. In the case of a functor, what is the least amount of data to build a meaningful structure that might also be empty, but don't be fooled by the fact that in our first example we used the e is equal to 0. Remember that for multiplication, e actually contains data in a strict sense because the e is 1. So it's not always that it's the emptiest value possible. So we need to provide something meaningful. Also notice that in eta, t is a type, and unit is the simplest type possible. So if f is a functor, we want here the simplest functor possible. And what's the simplest functor possible? The identity functor. I don't know if we have it. Let me scroll. No, we do not have the identity functor. So the identity functor is a functor that, well, takes as input a, and what's the simplest thing we can do with it? Nothing. Simply say, okay, that's the simplest functor. And then I'm going to copy this definition for the Liption, the list option, and map ID. Now takes as input a function from a to b, and returns a function from id of a to id of b. And well, this is the identity. Now, why the identity? Because this function here is the very same as this function here. Because id of a and id of b are literally a and b. And so whatever function we gave here, we simply return it. Notice, and this is very important, that the identity on functors, its mapping function, is the identity on functions. This is important. When these things happen, we really know this is a good definition, because the identity on functors and the identity of function, they are both identities. They are both the simplest things that don't really do anything on whatever input you gave. And as such, they have to be linked, because they are representing the same thing in two different domains. But these domains are similar, are related, are still computational and logical domains. So the simplest functor is id. Now we're getting somewhere. But eta, well, I mean, we can't really define we can't really define a function that takes as input a functor and gives us a functor back. So you could say that it takes id of a and gives us f of a. And this is, a generic function in a. But it also means that this is the same as function of a into f of a. Right? Because id of a is the same as a. This also happens to be a constructor. This also happens to be the constructor that gets a single value and puts it into f of a. We know that a functor is typically some sort of container. And so this says, give me the simplest possible container. And the simplest possible container, it's not the empty container, because that's too simple. The simplest possible container contains just one value. Because if it didn't contain any values, it wouldn't per se prove that it's a container. But eta is actually kind of a challenge. It says, okay, you want to be a monoidal functor, then you must be able to contain stuff. So here, I'm challenging you, I'm giving you stuff, I'm giving you this value here. Do something with it. And then we have an operator, a join operation. Now for the join operation, it's a very similar discussion. Now we have two functors that we have to somehow combine together. And one might be tempted to say, okay, yeah, you know what, let's do the same. Let's say that we go from a pair of f of a into f of a into f of a, which is attractive, because you could say, okay, get the contents of the first, get the contents of the second, and somehow pour them into the result. But this is not good enough. This is not good enough because if you look at this here, t and t are types, and pair is a generic type. So if you look at, let's say, the level of things, f is a functor, and pair is essentially it is a bifunctor. So that's the same thing. So we've increased the level of expressive power of the inputs, but we haven't done the same to the output. So that is not really correct. We want to combine, just like a pair of T and T combines the expressive power of two T's together. In this case, we really need to combine the expressive power of this F with this F together. The simplest way of doing this is to say that to have two containers merging their containing ability, we put them inside each other. By putting them inside each other, and we know that this is the functor coming from the composition of F2 itself. If you remember the Lipschon, if you look at the Lipschon here, it was a composed functor. It was created by composing list and option. And so here we are using functor composition to give rise to a new functor that has the expressive power of S combined with itself once. And this join operator is now saying something incredibly powerful, because now it's saying that F is not just able to contain, but if you put, let's say, a box in a box, so you have this level of nesting that creates extra structure, because now you have the outer box and the inner box, that this level of containment can be collapsed into one. And, well, so this is actually putting a lot of strain on the definition of the ability of F to contain stuff, because now it needs to be able to contain its own structure indefinitely, which is very similar to what we said here, because we said when you join a pair of numbers, it means that numbers are big enough that you can add two numbers, and even if you take the two biggest numbers you can think of, you add them, yes, you get a number which is bigger than them. And now we're saying you can take two containers nested inside each other, and it doesn't matter how complex the containment operation is, it doesn't matter, you can flatten it down into a single thing. That's powerful. For example, you could imagine a thread that gives you a thread back, and you can turn this into a single thread that waits on the outer thread and the inner thread and gives you the result back. And it requires flexibility. It requires a data structure which is, because the resulting thread must be as smart as the two original threads. That's a lot of power that we are requiring to these operations. As a first example, let's define a monoidal functor around, well, the identity functor. Why not? So we need eta ID, and we know that eta ID must be a function. Well, it's a generic function, so we need to use the usual trick of making it lazy. It's a generic function, takes as input ID of A, and needs to return ID of A. Or I'm going to use this formulation because I like the slight visual asymmetry that's kind of forcing us to see, okay, it puts the A into ID of A. And, well, what is this function? Well, it's the identity function. Why? Because it takes the A, which is already an ID of A, and, well, it simply adds an invisible structure around it. Adding an invisible structure doesn't really take a lot of effort. And then, a join of the identity, well, that's very similar. We take an ID of A, and we have to produce an ID of A with it. And what is this going to be? Well, again, I don't know if you want to take a guess, Moody.
ID?
That's still going to be the ID, because the input we get is ID of A. But if you look at this, ID of A is the same as ID of A, because this one here is A. But ID of A is also equal to A, and, well, we need to produce ultimately an ID of A, which is an A. Yeah, I mean, this is obviously the sort of the bullshit monoidal functor, but it gives a good impression. Now let's move to the next, and this is our first monoidal functor. Let's give another example of a monoidal functor. Let's consider the functions that take as input a number and gives us an a back. Sorry, I've written this completely wrong. Now functors. So we need functors in one single argument, in our case a, to define our simple monoidal functor. So I have to fix one argument and consider that a function that returns a value of a given type is sort of a container of these values, because you give it a number and you get an a back. So, and if you can get a's out of it, then you could imagine that in a very broad sense we have a container of a's. We couldn't do the same. We couldn't say a into number, because in this case fun_n is not a container of a. It's something where you can put a's in, but what gets out is a number. So in order for a functor to be monoidal, the easiest strategy is to make sure that it contains a's in some sense. Now let's map. So map fun_n now, and we take a function from ab into a function of fun_n of a into fun_n of b, and obviously now it's not the idea anymore. So let's build this. We take as input f, which is the function from a to b, and sorry, which is the function of a to b, and now we have to produce the resulting function in function of n of a into function n of b. So let's return this function. Now this new function takes as input the inner function, so I'm going to call it fn, and this fn, it takes as input a number and gives us an a back. So what can we do with it now? Let's take stock of our types. So f is a function of ab, and fn, I'm really going to put all the annotations here, fn is a function from number into a. And what do we need to produce? We need to produce a function of number into b. I'm going to do the very evil thing to get the compiler off my back for a second. So now at this point I'm simply stating, okay, if I look at the signature, I have one input, but then the next function, well, this is kind of carrying, the next function has this input. Okay, and then I have to define the result, and the result is going to be this function. Okay, so you know what, I'm going to define this final function, and this final function, it takes as input n, which is our number, and it has to return b, which is our final result. So I'm simply chaining all of these functions. Okay, so at this point on my line 83 here, I have f, I have fn, and I have n. So what can I do with them? Let's gain the ability to put multiple lines of code for the moment. So we can't really combine that many things. I can't call f at this point because I don't have a value of a. And I don't have a value of b yet, but I can call fn with n. So I'm going to call it temp1. So again, these functions that I've defined, that's the structure we have. We know it already. That's just from map. So this is for free. Now I simply take stock of all the inputs I have. So I've stated, okay, these are the inputs I have. I have this, and I have the input of the final function that I have to build. And from all these things, I must be able to produce a b. So temp1, well, I can call fn by giving it n. And what's the type of temp1?
A?
It's an a, yes, because fn gives us an a back. Okay, so now at this point, I have f, fn, and n. But I also have temp1. And, well, because we've also stated that we'd rather not use things twice unless it's needed, and we'd rather make sure that we use all the information we have available at least once before resorting to information we've already processed. So now we have f and temp1, which are the two things. Well, temp1 is fresh and f, we haven't used it yet. Can we combine them together? Yeah, we can call f with temp1. And the result? Hey, the result is a b. So now I can return the result. And there you go. That's the composition. Now let's prettify this a little bit, because this is obviously ugly. So now we don't need temp1, so we can call this right. Oh, we can call this right away, and we can return this in one go. So that's nice, and because we return it, we don't need for this to be a lambda, so that's very nice. But okay, so you kind of notice that this is taking an input, then calling fn, and then calling f on the result. So this is literally by definition fn, fn, then f. Okay, and that's kind of where we stop, because, well, can't really do much about it at this point now, or to an extent, because we could imagine that this. No, we really have to stop. So that's what it's supposed to look like, which is okay. Also notice that map fun, at its core, it's simply a fancy way of calling the function composition operator, which is very nice, which is very important, because it also means, again, we are on the right track. So that's the first monoidal functor we've seen. Let's take a short break, and then well, I'm going to get coffee, and well, I'm not going to record the break, so you can pause the video and see you in a bit. So now that we've seen the first two functors, let's move to yet another one, which also, well, these are all first simple functors that we're going to see as our first contact with the monoidal functors. And then we'll see some beefier ones in the next lecture. So we have pairs, and well, we could, for example, wonder, okay, can we make a functor out of a pair? First, let's begin with the intuition. So we have the pair, and the pair has two arguments. So we have to, like in the function, we have to fix one of these numbers. So let's say that our pair functor 1 is generic in one argument, and it's a pair of a with, let's pick number. And well, I'm going to pick number because number is a monoid itself, and so I'm kind of imagining that to make a functor out of something and a number, we're going to be confronted with these numbers at some point, and they will be annoying. And because of this, at least the fact that they're monoidal, the numbers themselves, that they have multiple monoids that you can define on top of numbers, is going to be handy. Now, okay, so we need map. So, well, you know what? I'm going to call it left, pair left, because it's a pair, so it puts a in the left argument. So map pair left, what is this going to be? I'm going to copy the signature once again, because it's very annoying to type manually. Map pair left, okay, it takes as input a function a into b, and it has to lift this function into a function from pair left of a into pair left of b. Okay, and again, what am I going to do now? I'm going to take all. I know I have to build this. So I have to build a function that takes as input. As the first thing, I'm going to copy it from this bit, because, well, I know it's exactly the same. It's a function that takes as input f, which is a function from a to b. And I have to return a function that takes as input, let's call it, well, p1, and p1 is a pair left of a. And now I have to produce a pair left of b. How shall we do this? Now p1 contains an a and a number, and we have to produce pair left of b, which contains a b and a number. I mean, without wasting too much time, we can build this right away, right? We can say that first is going to be, well, we call f, because f can turn p1 dot first, which is a, into a b, and second, what is second going to be? It's going to be p1 dot second. Or we could use the fancy JavaScript style spread operator, TypeScript style spread operator, which is the same, but for this we're not going to focus too much on TypeScript. Okay, so that's actually quite simple, and well, you could imagine that you could do exactly the same with pair right. But let's see if we can actually define the functor structure around, the monoid structure around it, because we need to define now the monoid structure around both. Oh, oops. No, we're going to get back into this in a second, because I realize now we took the break, we forgot to define eta for fun n and eta and join for fun n. So let's do it for our map pair, and then we go back to map fun n. Okay, so map pair left. Then we define eta pair left. It takes as input an a and has to embed it into a pair left of a. How do we do this? Now, we have an a, I'm going to call it a, and I have to build a pair left. Now, because it's a pair left of a, it's actually quite simple. I can say that first is a. What about second? Now for second, I'm going to put 0 now. It's a cheap choice and also probably a safe one, but we'll find out that there are multiple ways of defining pair left as a functor, as a monoid. Now, join, it takes as input a pair left of a and returns a pair left of a. Okay, so the first function, the function takes as input the pair left of pair left. I'm going to call it PLPL, and we have to give back a single pair left of a. Let's take stock of what's inside PLPL. What do we have here? I'm going to say that here we return a null exclamation mark as usual, very evil, but just to get less red on the screen. So we have temp1, which is which is PLPL dot first, and temp1 has type A. Then we have temp2, it's type A. PLPL dot first dot second, that's a number. Then we have temp3, oh, that's a number, that's not an A, And then we have temp3, and that's again a number, and that's PLPL dot second. Now, it is very fortunate that we only have one single value of type A, because we don't know what A is. So if we have multiple A's, we don't know where to put them. The fact that we have two numbers, that's handy, because how can I make a number out of two numbers? Now, fortunately, numbers have multiple monoids defined on top of them, so we're safe. So now I can simply return a pair where first is going to be temp1 and second is going to be temp2 plus temp3. Now, I really have to stress the fact that this here is the monoidal structure of sum in numbers, and this is the monoidal neutral element. So if I turn this into 1, this is not a monoidal functor anymore. This is. I have to turn the sum into a multiplication. So to be a monoid, it has to be a monoid all the way down, also to the content. And now I can remove a bit of these horrible temp ones and temp twos, and to try to get a bit closer to a slightly prettier one-liner. Wait a second. Yes, anyone PLPL dot second. Okay, then we can throw this away. You can disappear, and okay, now it's slightly prettier and a bit closer to what we want. Okay, so we know that pair left, and you can imagine also pair right, obviously, is a monoid if whatever we choose here as, let's say, the fixed value for pair left, if that also behaves like a monoid. And if we go back to the idea that second is 0 and here we add, well, you might recognize pair left as the container. which is one of the very first data structures we played around with in this course. Now, let's go back to the challenge of finishing to turn fun_n into a monoid. Because right now we only have proven that it is a proper functor, which I mean is already good, but not good enough. Okay, so A must return a fun_n of A. Okay, so we have an A, and what we give back here has to be, I'm going to put null exclamation mark for a moment, it has to be a new function that takes as input a number. So, okay, so we take the number, and I have to return an A. Which A am I going to return? Actually, simply be A. Because we have an A already, and, well, this function, whatever number it gets, it doesn't matter, because the fun_n we're building with eta fun is the stupidest of all. Now, there are plenty of functions that can build some A's given a number in an intelligent way, like getting the nth element of a list of A's. That's a meaningful eta fun_n. But in this case, that's a meaningful fun_n. But in this case, what is the stupidest fun_n you can produce if you're just given an A and no further context? Well, that's sort of the default constructor, which doesn't do anything with the n. That's the simplest implementation of fun_n. Just ignores the second argument. Let's see if we can join. Two fun_n's. So we have a function that takes as input a fun_n of a fun_n of A, and we have to turn this into a fun_n of A. Now, so the first function, it takes as input, well, this thing here. So the ff, I'm going to annotate it as a friendly reminder. And now we have to produce a single fun_n of A. Okay. Now, because we have all these functions, typically what I do is I keep digging down, I keep expanding the functions, because if I know I have to return a function, okay, I might as well simply say, okay, I return the function, and the function eventually will get as input an n. Okay, that's great. What do we have now? We have ff, and we have n. And, well, what can we do with them? We can't really do much. I mean, we can call, so ff expects an input of type number, so I can call it. I can simply say ff.f of n. But, well, this here is a fun_n that expects a number. I don't have another number here, but I still have the original one, so I can just call it with the same number twice. And this is a way to collapse it. It's actually quite simple. All right. So now we have seen how to go from monoids to functors. We have seen, how to extend the monoids into functors. What?
Can't we collapse the ff with ff then ff? Because it's applied twice, no?
No, because the output of this doesn't become the input of it. Yeah.
Okay, yeah, okay.
Yeah. Okay, so we've seen. We started with monoids. Then we extended the definition of monoids in order to be closer in line with our framework of functions. Then this more in-line definition, we expanded it to turn types into functors. And so now we have monoidal functors. The nice thing is that monoidal functors also come with another name. Monoidal functors are also known as monads. A monad is any functor with the definitions eta and join, and there are many of those monads. There are, well, actually, as a matter of fact, there are infinitely many monads. And the nice thing about monads is that all of a sudden they are quite capable of doing some nifty stuff, because a monoidal functor also has, for free, another operator which we call bind. If you look at eta and join, they're quite abstract. It's difficult to imagine how you could write programs by manipulating eta and join directly. So, and the most common operator that we find in monads is bind, which says, okay, so suppose you start with a value bound inside our monad, m of a. And this value, this value p, well, we want to put it into a function that takes as input a, so the content of p, not p itself, and gives us back an instance of the monad on b, and then we want to get m of b as a result. Now this is slightly more usable. Why? Because it's saying, okay, if you have a monad of a, and you have something that depends on whatever comes out of it and gives you a monad of b, it simply gives you the monad of b back. Almost everyone who's been active in the JavaScript world might have recognized the fact that this bind operator looks a lot like the then operator of promises. So suppose that you have a promise, which is basically a thread that gives you an a back, and you want to do something with what typically we call, well, I like to call this k, and we have something that we want to do when the promise is done. And this is, well, this gives us a promise as well. Then you could simply say p then k, or which in our case is the same as bind pk, automatically. And the nice thing is that then or bind, which are exactly the same thing, can be defined directly from join and map. Because we know that here with bind we have map, we have join, and we have eta. Now, how do we define bind in terms of map and join? I have this function here. So the first attempt could be, okay, so first of all, let's take stock of what we have. We have p, we have k, we have p, k, we have map m, we have join m, we have eta m. What's the first step? Now, we could say map m over k. And what's the type of map m over k? It's a function that takes as input an m of a and gives us as output, think about it for a second, no, not m of b. Because k takes as input a but gives m of b. And map adds m on both sides. So if k is a to m of b, what we get back puts m on both sides of this function. So we get m of a into m of b. This goes from m of a into m of b, because it puts the m around both. And, well, what can we do with the result of this? So now, well, we have map k, and it wants an m of a. Do we have an m of a? Of course we have it, that's p. So now I can call map m of p, and all of a sudden what I have is an m of b. But what I want is an m of b, and I have nesting. How do I fix the nesting? I join. And now I get the m of b I wanted. So, and actually, you can clearly see that, well, this is simply, essentially map m, then join m. So bind is just first you map, then you join. And notice that even though I've made an example here, what am I doing? Even though I made an example with promise, this does not require any specific knowledge about which monad we're talking about, as long as it's a functor, as long as it's a monoid. So if it's a monoidal functor, then we have a bind operator, and then we have a then operator. So let's consider, for example, pair left, and let's define this bind pair left as this generic function takes as input p, which is pair left of a, and then we have k, which is a function over from a into pair left of b, and it returns pair left of b. Okay, and again, let's have the compiler shut up for a second. Okay, so what I said is roughly this. So let's invoke map m over k. So const temp1 is map m, well, we can call it directly, over k. Oh, map, yeah, obviously map pair left. And map pair left, map pair left, oh yes, and then we call it over k. So now it's complaining a bit because we have to be more specific with the types. So map pair left wants two parameters, a and b. It wants to know, okay, what are the inputs and the outputs of the function we're going to pass. The first input is a, and the second input is pair left of b, because that's simply what k gets. Now, what's the type of temp1? Now, the type of temp1 is a function which has these as parameters with m added around them. So it's not a into pair left of b, but pair left of a into pair left of pair left of b. And now it's happy. So we have this function temp1, and now we can call it. We can say temp1.f, because now we have a p, we have a pair of a number, which is what we need. And now temp2, it's simply whatever temp1 has returned. There we go. And now we have temp2, it's one pair too much. You could say that temp3 is simply join pair left, and then we call it on top of temp2. Now again, oh, the intelligence is marked enough here. Oh, because it's not a lambda. Okay. And now temp3, it's simply a pair left of b, isn't it? That's what I would expect. So let's tell it that the content is a b. Yes, now it's happy. Okay. And now temp3, oh, what do you know? That's exactly what we were supposed to return. Okay. So, well, now we could do at the very least a little bit of inlining, because otherwise this is terrible. This really hurts the eyes a bit. This really, okay, it looks slightly better. Let's see now. Well, this does really look like map pair left f of k, then join pair left. So, you know, let's try it. So at some point we will have to give this to decompose the result. So then, and then the f and the join pair left, we simply put it in, and it's actually happy. So it because it makes sense, you know, that this is saying, okay, first you have to give k to map pair left, because it needs to map something, and whatever comes out of it, you join it, and well, the parameter simply goes to the back. And if you wanted to bother to make this into a properly carried function, where first we take p, then we take then we return a fun that takes k, etc., then you could make this slightly prettier. But at some point, well, it's not. At some point, it's not worth the bother that much. And you know that bind pair left, you could simply take it, and you could go to, let's say, no, not this one, sorry. to fun n, and now you could say no, for whatever you have. I would like to do search and replace. Can I? Just moved to Mac recently, so now I'm no. Okay, so search pair left and replace with fun n. No, I don't want to do it everywhere. No, okay, I'm going to do it manually. Okay, so pair left fun n. Pair left is fun n. This is fun n. This is fun n. Now, obviously, map has to be over fun n. Oh, did I put a capital M? Seriously? Did I put it everywhere? Oh, okay. So it's a capital M. Then obviously this is fun n, and this is join fun n. And we are certain that because fun n is also a functor, and it's also a monoidal functor, that we have these functions, and that's it. And this means that we get bind fun for free. Now, we've also seen that we could define a framework of functors with type safety. I'm not going to show it here because it really is outside of the bounds of this course, but you could imagine that you could simply define bind like we defined map a few weeks ago. It was, I think I have it here. Yes, it was in this bit that we were able to simply define the map function just once with safety, and you could say bind as long as M extends key of monads of A, and you could simply define the bind function literally just once, and have the compiler and the language take care of the definition for you. But even if you were to resort to copy pasting, which is, the language can do better obviously, but even if in another language you were to resort to copy and pasting the definition of bind, it's okay because you don't need to think about it, and you're sure you just have to do some very minor syntactic change, and that very minor syntactic change results in guaranteed working code. And not only working code, but also code that still respects these relations. So let's take another short break, and then we'll move on to the closing of the lecture. Yeah. Okay. So, for the last stretch of this lecture, I'd like to discuss two last things. I'm not going to discuss, because that is going to be a big focus of the next course, what these equivalences become when turned into functors. I will talk a little bit about an alternative formulation of the bind operator, because we have these three operators, and bind is nice because bind allows us multiple compositions. You could do something like this. Suppose you have P, and then you want to extract the value, so you could say XP, and then you could add, suppose you have another instance, let's say you have Q, have XQ, and then you go for yet another one, so you could say bind R, and I have XR, and ultimately you keep, you just combine all of these values that you have extracted from the monads. So bind is a way of saying, okay, you have P, you have Q, you have R, and you want to do something with all of their results. So bind simply says, okay, I'm going to call this function here as soon as I have managed to extract the value XP, or the values, because this function might be called multiple times if P contains multiple values, for each value that P spits out. But then you do the same. So this is a way of introducing an order of evaluation, first of P, then of Q, then of R, and then here we have, oh sorry, this was supposed to be a comma, and here you have XP, XQ, and XR, and you can do whatever you want with them. And well, finally you could combine by calling ita, you could combine something that does something with XP, XQ, and XR together in some value that then you re-encapsulate into a new instance of the monad. And this is very common, and if you stick to the JavaScript promises example we had before, then here you would say p.then XP, and then you would say q.then and xq and r dot then and xr, and then, well, there you go. And this, and all of a sudden we are in the, oh, and here you would have something like promise dot resolve, if I'm not mistaken. I think it's called the resolve. Or this could be select many in link. And I have no idea how to encapsulate this, what that becomes. Or this could be, I think it's actually called the then, or continue with, in the task parallel library in C#, where P, Q, and R are threads, and this would be, I think, task.complete or something like this. So, and now all of a sudden you see, oh wow, these are all monads. Yes, absolutely, because not only are monads, are there infinite monads, they are very common, and not only are they very common, they are the tool of choice of our industry and of our sector for tackling complex problems. So the fact that monads do exist already and that we actually use them without knowing that they're monads simply shows that we're kind of using these very powerful constructs blindly without really knowing what they do, but we need them. No one in their right mind, well, I mean, I guess there must be a developer somewhere that spouts this kind of bullshit, but no one would say, oh, we don't want promises anymore, just give us hardware interrupts or lower level stuff. So we need these things, and they're very powerful, just as link in C# is incredibly powerful, to task parallel library, etc. And the alternatives are so much more painful. And monads, by virtue of telling us exactly, okay, what does it take to be a monad? You need to be a functor, but we know you don't just happen to be a functor, you have a map function. The map function must respect composition and identity. All of a sudden we have a lot of rules to tell us when are your promises. If you were to implement something like promises or whatever, or other constructs that encapsulate promises like we will see in the rest of the course, what do you need to check to be sure from with mathematical certainty that your implementations make sense, that your implementations do correctly encapsulate a logical thought instead of just being, a random rambling. Now, and before closing off, I'd like to show another formulation, which is the formulation of Kleisli arrows. So a Kleisli arrow is something that returns a monad. So Kleisli over M of A is a function from A into M of A, where M is a monad. And we could define the then operator over a monad as taking first F, which is a function from A into M of A, into M of B, and then G, which is a function from B into M of C. And you might have noticed this looks a lot like the signature of then, because the then over functions takes a function from A to B and then a function from B to C. And what do we get back here? What do we expect to get out of this? It's going to be a function from what to what? From A into
function?
No. Into M of C.
Oh.
Because it's the symmetry, right? And now how do we implement this? Okay, so we have here F and G, but we also have eta of M, we have join of M, and we have map of M. Okay, so so we have F, we have G, we have map M, we have join M, and we have eta of M. All right, so you could say, okay, F then, because we can't really call F, right? Or no, you know what? Let's keep this simpler. We have to return this function. So fun that takes as input an A. And now in here I have somehow to return, so A has type A, and I now have to return an M of C. Okay, so now here I have all of these things I had before, but I also have A. So now you could say, okay, I can, well, this is just a comment, so I'm not bound, because to define this I have to follow the higher order types approach we had for functors before, but we're not going to do it now, obviously. So now, well, the only thing I can do is I can simply call f with a. So I could say temp1, which is type m of b, is f of a. Okay, and now I also have temp1. And temp1 is m of b, and that's the problem. I can't really call g with temp1, now can I? I can't, because I want to bind g to temp1. Okay, so that's great. So temp2 is bind temp1 and g. And what is this going to what is this going to return? That's going to return an m of c, which is exactly what we wanted. So now I can simply return temp2. So you could say bind temp1 over g, and that's just what we return. And now we don't need any of these things. Alright, and obviously because we know that bind is simply defined like this. Now this is f of a, and this is g. So these are this is the Kleisli arrow. And the beauty of the Kleisli arrow is that, for example, we could, so the Kleisli arrow, it allows us to define, to take this rule. I'm going to go back and to take this very old rule that we had over the monads, and it allows us to simply redefine the, this law of monads just in terms of then f over eta and a function f is the same as then f over function f and eta, which is the same as f. Which really makes sense, because what is then what is the more, because what does then m do? It actually takes whatever f created, unpacks it, puts it into g. And because eta doesn't really pack anything, or that doesn't really add any structure, it basically just does the minimal amount of wrapping, this is simply going to put whatever you wrapped with eta into f directly, which results in whatever f did. And this does the same, but on the output side. So this is the very same as when we said that then idf is the same as then fid, which is the same as f, and this is actually the Kleisli equivalence over the identity monad. So you slowly see that things are all recomposing back into each other. But again, to come to the conclusion why this is the case, we're going to do it. We're going to see it in the next course. Now, thanks a lot, guys. Obviously, well, I can't ask you if you have any questions, because that doesn't really help when recording lessons online. But the best of luck, and well, until next time.